Welcome to i9 Global. Join us as we delve into the basic foundations of artificial intelligence. Today, we're going to explore on the topic computer vision. What is computer vision? Computer vision is a transformative field of artificial intelligence, AI, that empowers computers to see, interpret, and understand visual information from the world, much like humans do. This technology mimics human visual perception through algorithms that analyze images and videos, enabling machines to recognize patterns, detect objects, and even interpret complex scenes. With the rapid advancement of machine learning techniques, particularly deep learning, the capabilities of computer vision have expanded dramatically, allowing for unprecedented applications across various industries. One of the most notable applications of computer vision is in the realm of autonomous vehicles. By leveraging a combination of cameras, LiDAR, and radar, these vehicles can navigate complex environments, recognize obstacles, and make real-time decisions to ensure passenger safety. The integration of computer vision in transportation systems not only enhances efficiency, but also paves the way for smarter cities, where traffic management can be optimized using real-time visual data. In healthcare, computer vision is revolutionizing diagnostics and patient care. Advanced imaging techniques, such as MRI and CT scans, can be analyzed with remarkable accuracy using AI algorithms, enabling early detection of diseases like cancer. Additionally, computer vision systems can assist in monitoring patients remotely, ensuring timely interventions and reducing the burden on healthcare professionals. Retail businesses are also utilizing computer vision to enhance customer experiences. By employing facial recognition technology and analyzing shopping patterns, retailers can personalize marketing strategies and improve inventory management. This data-driven approach not only boosts sales but also fosters a deeper connection between brands and consumers. Computer vision plays a critical role in security and surveillance. Intelligent video analytics can identify suspicious behavior in real time, alerting security personnel to potential threats. This proactive approach to safety has become increasingly vital in public spaces, where the ability to monitor vast areas efficiently can deter criminal activities. In simple terms, we can say computer vision enables computers and systems to see, interpret, and understand visual information from digital images, videos, and other visual inputs, much like humans do. It involves training machines to extract meaningful information from visual data and then use that information to make decisions or take actions. Here's a breakdown of what that means. Mimicking human vision. The core goal of computer vision is to replicate the complex capabilities of the human visual system, but at a speed and scale impossible for humans. Processing visual data. This involves acquiring images from cameras, sensors, medical scanners, etc. Pre-processing them, for example, resizing, noise reduction, and then analyzing the pixel data. Extracting meaning. Instead of just seeing pixels, computer vision systems identify and understand features like edges, shapes, colors, textures, and patterns. What computer vision does: recognize objects and faces. This is fundamental to many applications, from security to image tagging. Detect movements or changes. Crucial for surveillance, activity monitoring, and even gesture recognition. Understand scenes and environments. Allows for context. Aware applications like autonomous navigation or smart retail. Interpret visual data to make decisions. The ultimate goal: enabling machines to act intelligently based on what they see, whether it's stopping a car, sorting products, or flagging suspicious activity. How computer vision works. Basic flow. Breakdown of the basic workflow of a computer vision system. Each step is crucial and builds upon the previous one to achieve meaningful interpretation of visual data. 1. Image, video input. This is the starting point, providing the raw visual information. 2. Pre-processing. Essential for preparing the data for analysis, removing noise, and standardizing it. This step significantly impacts the quality of subsequent analysis. 3. Feature extraction. This is where the system starts to understand what's in the image by identifying key characteristics that distinguish different objects or patterns. 4. Model processing. This is the brain of the operation, where a pre-trained AI model, often a deep learning model like a convolutional neural network, applies its learned knowledge to interpret the extracted features. 5. Decision output. The final step, where the system provides its conclusion or takes an action based on its interpretation. Computer vision's applications. 1. Facial recognition. Identifying individuals in photos or video feeds. 2. Object detection. Locating and classifying objects. For example, cars, people. 3. Medical imaging. Diagnosing diseases from X-rays, MRIs, etc. 4. Autonomous vehicles. Understanding surroundings using cameras. 5. Augmented reality, AR. Blending real and virtual objects in real time. 6. Surveillance systems. Detecting unusual activities in public places. 7. OCR. Optical character recognition. Reading and digitizing printed or handwritten text. Core technologies in computer vision. Convolutional neural networks, CNNs. These are central to computer vision, mimicking human vision to process pixel data. CNNs use multiple layers of filters to automatically learn hierarchical features from images, greatly improving the accuracy of object classification and recognition. Deep learning and transfer learning. These enhance CNN performance. Deep learning trains multi-layered networks to extract intricate patterns from large datasets. Transfer learning adapts pre-trained models to new, specific tasks, speeding up development and boosting accuracy, especially when data is limited. Image processing techniques. Methods like filters and edge detection pre-process images, highlighting crucial features and improving image quality through techniques such as histogram equalization and noise reduction. This helps CNNs more accurately identify and classify objects. OpenCV. As a leading open-source library, OpenCV provides a wide array of tools that simplify the implementation of complex computer vision algorithms. It's essential for rapid prototyping and developing sophisticated applications, from facial recognition to augmented reality. Advanced object detection models. Architectures like YOLO, You Only Look Once, SSD, Single-Shot Multibox Detector, and faster RCNN have revolutionized real-time object detection. YOLO, known for its speed and accuracy, efficiently detects and classifies multiple objects simultaneously, making these models ideal for applications like autonomous driving and surveillance. Computer vision is a rapidly advancing field with a vast array of applications across industries, including autonomous vehicles, healthcare, medical imaging, security and surveillance, manufacturing, quality control, retail, and augmented reality. That brings us to the end of this video. Up next, we'll dive into robotics and autonomous systems. Don't forget to follow, like, and share. If you have any questions or suggestions, feel free to drop them in the comment section. Thank you.